We're here. The Purdue team is here. Let me get rid of this. Thank you, Avican. All right, next slide, please. You're in charge of that.
Okay.
All right, funding for today's broadcast and the following message is provided by Culture Hacking. Do you have a message you would like to convey, but conventional social exchange makes communicating your idea difficult? Try Culture Hacking today with one of our low-risk 30-second trials. Find an open mic near your chosen audience. We recommend raising your hand at a Q&A session, and then people will know what you want to know. Culture Hacking, it's what you're about to watch. This is the WNCOST Lightning Round Radio Show, and I'm your host, Bob Kenley.
I think because lives lived in that alignment
more exciting, more dynamic, more joyful than any other way we could choose to live our lives.
Intuitive that a group of engineers would be able to help as well.
Good day and welcome to the live broadcast of the WNCOST Lightning Round Radio Show. I'm your host, with the host, Professor Bob Kenley from Purdue University. Our guest today is a doctoral student from Purdue University, Avican Phillips. He's currently pursuing his PhD in industrial engineering from Purdue, and his research focuses on the verification and validation of AI-enabled systems and connected autonomous vehicles. He's here to talk about loss-driven SE and ASELCM patterns for connected and autonomous vehicles. Avican, thanks for coming on the show today.
It's my pleasure, Professor Kenley.
So you are looking into evaluating AI-enabled systems, especially applications in self-driving cars and the like. What is the motivation going into this?
Thank you, Professor Kenley, for this question. Artificial intelligence has been relied upon by self-driving vehicles to understand the environment and traffic conditions towards making safe driving decisions. But since these systems are safety critical, then it's no surprise that the impact of AI on AV safety needs to be addressed. And certifying this kind of systems, it remains a research challenge, and it must be solved if we want to actually achieve the commercial rollout of this kind of systems.
Wow. We hear a lot about the shortcomings of self-driving cars and AI-based systems in the news nowadays. How crucial is certification, as you mentioned, in ensuring public trust?
Well, the certification of AI systems can help strengthen trust in technology and application, no doubt about that. And again, this is definitely going to increase AI applications. But the goal of a successful certification process should be to guarantee the standards and at the same time avoid overregulation and enable innovation. So, however, we need to figure out how to test, verify, and validate these AI systems efficiently and effectively for certification to occur. A while ago, I was checking on YouTube and I found a Tesla enthusiast who was actually talking about his Tesla Model Y's full self-driving FSD beta technology on snowy roads. Interestingly, this guy, he took his new Tesla vehicle on the loop where he previously tested his FSD technology and it worked out well during good weather. Now, when it started snowing, he couldn't trust his FSD technology again due to certain situations. Okay, the first one, there was, the poor road visibility. The poor road visibility, especially the surface visibility during snow, actually hindered and flustered this technology. Again, during this, when there's snow on the road, again, and you're driving, you notice we have varying grip conditions, So again, these two reasons are kind of why, the FSD technology wasn't really working great. So at the end of the day, this leads us to this conclusion. How do we address this kind of a traditional question where we're asking, okay, are we building this system? Are we building this system right? And are we building the right system? So, yeah.
Oh, that is interesting. It seems more needs to be done to bridge the gap when evaluating these systems.
Yes, there is a need to evaluate the intelligence of the vehicle to decide if the CAV can operate safely and efficiently without human intervention. Okay. And for self-driving cars, for example, the desired goal is for these cars to drive more safely than humans, for us to have fewer, fatalities and crashes.
So what is the state of the art in terms of the safety verification of autonomous vehicles?
Oh, okay. Thanks for this question, Prof. Kenley. Interestingly, a lot of research has been done on the intersection of AI and AV safety, but most of them have been computational in nature, and they haven't imbibed the safety engineering culture as it is. So again, I found only a few studies that's focused on 3 topics, positioning AI as a potential source of, negative impact on safety. That's we're talking about fault forecasting, ethics, and policies, and then the issue of dependency and trust. But while most studies will always project AI as that branch, that discipline that has a positive impact on AV safety. However, AI methods are currently being utilized in addressing safety issues for CAVs. So, and one thing we need to know is by actually utilizing AI with these systems, then definitely we have an inherent inapplicability of traditional verification systems approaches for certifying the systems. So that's one of the things we see nowadays.
I see. So when you say traditional, do you mean these AI systems are different from the type of systems the SE community envisioned when coming up with the system development lifecycle process models? Like the V model, where verification is indeed a crucial step?
For most part, I would say yes. Again, a lot of there's a work by Shadab and some other systems engineers who, they provided a system theoretic perspective on verifying AI-enabled systems. Now, traditional systems, you can best describe them as behavior preserving. That is, when you subject them to the same inputs, the system will produce, a predicted output. And these are deployed in environments with little or no learning. So they're pretty straightforward. Now, things get different with AI-enabled systems, especially because they have, AI capabilities that can leverage historical information in altering the operational parameters of the system. So while V&V activities are employed to ascertain or gain confidence about the future behavior of a system in its operating environment and context, the inherent complexity and uncertainty with these systems render the traditional V&V approaches unsuitable for this kind of systems.
How does loss-driven engineering come into play with all of this?
Well, safety is one of those loss-driven specialty areas that focuses on human life and health. Also, we're talking about environment assets and other things that could be lost in this situation. So in terms of the loss types considered under this specialty area, the loss of life, reputation, loss of public trust, these are just some examples and the beginning of potential losses if we don't get these V&V activities right for AI-enabled systems.
This sounds like a vast body of work, especially with the gap in what needs to be done in evaluating AI-based systems.
That's true. I agree with you, Prof. Kenley. I'm interested in the external aspects of verification for AI-enabled systems.
So what do you mean by external aspects of verification? Can you shed some more light on this distinction?
Okay, sure. Of course, the inherent challenge of formally verifying the systems is being recognized as internal and external in literature. Now, when we say external, we're talking about addressing challenges that cover the modeling of the CAV's physical environment and verifying the behavior of this kind of system within that operating environment. But then again, this kind of challenges are the ones that actually present, potential issues with presenting sufficient evidence, to the public for both certification and public trust in operational situations. So that's why I'm kind of interested in this particular aspect. So specifically, I'm talking about when we're looking at the loss-driven engineering, when we're looking at the goal of external verification regarding loss-driven SE, and this maps perfectly with the SE principle of trying to control unavoidable hazards, including assuring transitions from one non-acceptable mode or state to another.
That sounds more clear now. You can expand on the external verification that you started on a little while ago.
Okay, thank you. Within this verification classification, it's essential to understand that we have different perspectives on problem modeling, and two major views when we're talking about external verifications are the computational perspective and the system descriptive perspective. And when I say system descriptive, I'm talking about the ones that are related to MBSE. So.
Okay, so with these two significant perspectives, do we have the best or the most preferred?
That's a tricky question. I wouldn't want to say there's a best perspective, but again, it depends on, based on the researcher or the modeler's background, they will have their own way of viewing those perspectives, although it depends on their bias, their technical background, and other things like that. For me, I see things by looking at both perspectives and thinking about the common ground between them. And because it's only when we start thinking like this that we can build a universal structuring for the problem. Now, let's imagine something. Imagine for all of us over here, someone decides to just blindfold everyone, and then you're placed, at different sides of an elephant. So someone is holding the trunk, so you're blindfolded, and probably someone is blindfolded, and the person is holding the trunk, the elephant's trunk. Another person is holding the elephant's ears. Another person is holding the tail. Another person holding the, one of the legs. And then they ask you, they just ask everyone a question. So what kind of animal is this? We'll have a lot of answers, different answers, definitely. So, I'm just trying to give this analogy to just explain, the different perspectives people have when it comes to working on this kind of problem.
Okay. So what does the system descriptive modeling perspective really look like?
Okay. For that, when we talk about, let me start by saying agility is one crucial survival trait for an AI-enabled system to adapt to uncertainties and changes in the environment. The Agile System Engineering Lifecycle Management, that's the ASELCM framework. It's an MBSE-based Agile SE lifecycle pattern, and it's been utilized in modeling AI-enabled systems, especially when you look at their performance couplings, the underlying relationships, and etc. Well, furthermore, other systems modelers have integrated the digital twin concept within the MBSE framework to address these verification challenges.
I think you have a slide on that. Oh, there it is. So I am interested in more information about the ASELCM on this slide. So how does the ASELCM model frame the autonomous vehicle as an AI-enabled system? I don't see it there. Oh, there it is. Okay.
Yes. So in this slide, which you can see on the slide, you can see there are 3 system reference boundaries containing 6 subsystems reference boundaries. Interesting. Now, for system 1, we have the autonomous vehicle as the engineered system right now, and for system 2, this is encompassing the target system. Now, when I say the target system, I'm talking about the engineered system, which is the CAV, and its life cycle components within a particular operating environment. Now, in system 2, the target system will be functioning within the target environment, and it's going to be managed by the life cycle manager of the target system. Now, the learning and knowledge manager for the target system is responsible for the learning process in system 2. For system 3, the learning will also involve the extraction of knowledge and data from testing experiments, traffic scenarios involving this engineered system, which is the autonomous vehicle.
Interesting. I noticed from the diagram for both systems 2 and 3, there are two capabilities, one for learning and the other for lifecycle management. Why is that?
Thank you for that question. That's a very good question. Now, this is one interesting upgrade on the traditional VMV for SE systems that are behavior preserving. That is, there's nothing to be learned. And then we're moving them into AI-enabled systems. Now, for the one on the, if you look at systems 2 and system 3, and you look at the boxes on the right-hand side, which is the one with, the 3 colored gears, you notice that those ones are actually the life cycle managers for systems 2 and systems 3. And they're all about just agile movement within what is already being known. So again, this is what a traditional VMV will handle. But then the ones to the extreme left, that's the ones that are concerned about learning and knowledge management, pardon me. Those ones are they're concerned about, how do we extract knowledge from experiments and observations? How does this engineered systems actually learn from the environment and things like that? So this is where the learning is needed to ensure agility of an AI-enabled system.
Wow, that was an insightful explanation.
Thanks.
So, you have talked about the system descriptive perspective on external verification. What about that computational perspective?
Well, for the computational perspective now, there's been some work when it comes to external verification. There's been some work on the utilization of formal methods, and this has been used a lot in computer science for verifying, software and some other things like that, where they use SAT, satisfiability, modulo solvers and things like that. Also, within the computational perspective, most times the emphasis is usually on the dynamical behavior through time-based simulation, optimization, numerical methods, simulation platforms, and things like that. In this slide to your left, you have the adaptive testing scenario library generation framework. It's from it's from a computational work by Feng and his group. It's just a process for navigating the testing and evaluation from the generation of a testing scenario library. And it's when this library has been generated that the CAV can actually be evaluated. Now, the scenario decision variables, for example, highway exit, or you want to cut in, that's a scenario. I mean, we have different scenarios. These are formulated by different scenario by different scenario decision variables. So, and when we're formulating this problem, we also consider the operational design domain. So the incremental performance metrics are designed, including safety, functionality, mobility. And at the end of the day, a method is proposed to actually generate the testing scenario library for further optimization.
Thanks. So on the right-hand side there, I see there's a surrogate model and there's an autonomous vehicle being tested. What's the difference between those two?
Well, in the computational work being done by these guys, they considered limitations in the different scenario types that can be handled. And CAV models can be applied for performance metrics to be evaluated, right? But then they also proposed a systematic framework called the Adaptive Testing Library Scenario Library Generation, the ATSLG, to overcome these limitations, where each testing scenario will be evaluated by a newly proposed measure, which is the scenario criticality.
Ah, that's interesting. So on the next slide, you bring up the real world and the surrogate models. How do these work?
Yes, this is it. So the framework, the ATSLG framework permits the utilization of a surrogate model, since the exact CAV model isn't really available most times in testing. However, the performance dissimilarities between these two systems, which is the surrogate model and the CAV model, under evaluation, these performance dissimilarities actually exist, and they can lead to the generation of suboptimal scenarios. So at the end of the day, the modeler will want to run an optimization of critical decision variables based on the suboptimal scenario libraries. So for illustration's sake, the surrogate model, the surrogate world is created as a proxy to the real world.
Oh, now that you've shared how the two major perspectives works, can parallels be drawn about how the systems and computational models structure their verification aspects?
Yes, I believe there are interesting parallels to be drawn that demonstrates shared perspectives between this major approaches of looking at the verification problem. As I explained earlier, a surrogate model, I mean, it can be viewed as a meta model or an autonomous vehicle, a CAV emulator that is trained using a data-driven approach. Now, this is a concept that is utilized by computational scientists and engineers for uncertainty management and quantification. But this line of thinking, in my own opinion, can be used within the digital twin technology, which has been conceptualized by some systems modelers and captured within the MBSE framework.
So you're saying those surrogate models are a subset of digital twins?
I wouldn't want to go far to saying that, but I would say a digital twin is it's a virtual representation of the physical system, and the physical system can in turn be seen as a biological twin, of the digital twin. Yeah, this is kind of interesting. But in emulating the behavior of physical systems, it's critical in understanding how AI-enabled systems actually behave within their operating context. Now, the difference between the digital twin and a computer model is that the digital twin updates itself to track the physical twin through sensors, data analysis, machine learning, and all those other approaches. But ideally, physical and digital twins must also approach what we call temporal synchronization. That is, ideally, digital twins are likely to yield erroneous results, especially when data collected is corrupted by complex noise within the operating environment. Now, this is where surrogate models can come in. And since they are computational models that are considered as a proxy to the actual high fidelity models, then they can be utilized to actually, quantify the uncertainty being generated by this noise within the operating environment. And in answering your question, I would say surrogate models can be deployed within the analysis of signals to be sent from a digital twin to the physical system. But they can also be deployed to support data functionality within the digital twin technology too. So that's kind of how they relate.
So now going back to the shared perspectives, are there other parallels to be drawn between the views?
Yes, there are other perspectives to be actually derived between these two major approaches. For example, when we talk about shared perspectives, you're talking about the first one, let's talk about phenomenon, interactions, operating conditions and things like that. Thankfully, both perspectives have been able to agree on different scenarios as, one of these kind of interactions. So a traffic scenario like a cutting scenario, a kind of an highway exit, like when the vehicle is trying to exit out of an highway, that's a scenario. But scenarios like this have been, everybody, both the system descriptive and the computational guys, they both agree, yes, we do have traffic scenarios, and these are things we can actually approach. So for the second part, we've got, in terms of when we're looking at shared perspectives, we're also talking about attributes and variables. And it's a good thing because both perspectives actually agree on the type of performance measurement and evaluation. So things like safety, functionality, mobility, these are examples of, shared perspectives between these two approaches. Then again, the last one is dependencies and laws. And when we look at things such as road signs, for example, road signs is kind of, one of, for example, road sign, it's a kind of a dependency to be considered during modeling because it's vital to kind of map out all these shared perspectives between both modeling worlds to define and refine any kind of AI-enabled systems modeling problem, such as the verification challenge. So as much as we try to attack or address the problem from different perspectives, eventually we're solving the same problem, and I mean, there's a need for shared perspectives, but then again, there's been a lot of work being done within MBSE towards extending traditional V&V activities, which, I mean, couldn't be used in just traditional SE systems. There's been a lot of work being done in trying to extend these approaches towards AI-enabled systems. So that's...
Okay, well, folks, that's all the time we have today. Until next time, I'm Professor Bob Kenley, and this is the WNCOSE Lightning Round Radio Show. This is the WNCOSE Lightning Round Radio Show, and I'm your host, Bob Kenley.
I think because lives lived in that alignment
More exciting, more dynamic, more joyful than any other way we can choose to live our lives.
Intuitive that a group of engineers would be able to help as well.
Cut.